And so this PowerPoint is going to be about um, introduction to digital imaging. And so a lot of these terms we have to know, okay? And so when we look at terminology, these are the terms that the ART defines as what we should be considering when we're going through questions. Everything's going to be based off of this area here, okay? And so when we talk about things like digital radiography, computer radiography, direct radiography, all the terminology needs to be assessed. And so whenever you hear the term CR, that is computed radiography. When you're looking at direct radiography, DR, that is the systems where we get an instantaneous readout. And so there's different differentiations between those two systems, right? And so we're going to talk about those later. When we talk about spatial resolution, this is called sharpness. This is the sharpness of the structural edges on the image. Okay, and so that's what we see. Receptor exposure, when we look at it, that is the amount of radiation striking the image receptor. Brightness, when we talk about brightness, um, brightness is referring to the monitor. And so when we are talking about the monitor, um, just like on your iPhone or just like on your laptop, you can change the brightness, right? And so that's what we're seeing here. Contrast is just the visible differences between two areas, so we haven't seen a change in in that area. Dynamic range establishes the range of exposures that we can utilize. Exposure latitude is the range of exposures that gives us a good image. And subject contrast is just the information that we see and the contrast we see between the tissues in the body. And so these are standard definitions. This is actually a attachment that's found on the content specs for what we need to complete. Now, when we discuss spatial resolution is the term that we use to describe how we can see these small, high contrast structures or objects. Okay. And so there's a variety of different controlling factors in this: size of the matrix, pixel size, field of view, detector element size, sampling frequency. Um, and so when we look at it, spatial resolution is a limiting factor in DR. When we look at it, there's certain elements of spatial resolution that will cause us to not be able to image properly. And we're going to talk about those things. But the biggest thing you need to know is in DR, it's going to be the detector element size. Okay. And in CR or computer radiography, it's going to be the sampling frequency. And so when we talk about um, things to note, we are looking at our terms here of matrix and pixel. A matrix is the combination of rows and columns of pixels. The pixel itself is the smallest component of a matrix. And so when we look at this, this is a matrix, this box here. And then the smallest part of that matrix is the pixel. It's an individual piece here. And so pixel size, when we discuss things, the smaller the pixel, the better the spatial resolution. And then pixel pitch, the spacing or distance between the pixels. So when we look here, I pulled out the arrows to showcase. With A, what we're seeing is a smaller distance. Whenever we have smaller distance between pixels, we get better resolution. And so we're looking here. This statement is probably the biggest thing that you need to know. All right. Larger matrix, lower pitch, smaller pixels, all of those things will equal better spatial resolution. And so what we're seeing here is, and for example, in figure C, we have the smallest pixels, right? You see all these small pixels. Now, when we look here, there's about 9 pixels, right? That could fit probably in one box in A. And so when we look at that, what we're seeing is that in C, where there are 9 pixels, each one of these 9 pixels would be given its own shade of gray, right? Depending on what we're imaging. Now, when we are over here in image or matrix A, what we're seeing is that one pixel right here would only get one shade of gray. So instead of 9 different shades, we only get one. So everything becomes less sharp because when we look at it, what we're seeing is that we wouldn't be able to distinguish all 9 of these blocks, right? We would only see one block that's an average of all the shades. And how that looks when an image presents itself is here. So look at this matrix with 2000 by 2000 amount, right? And then here is a 64 by 64. Now, when we look here with the 2000 by 2000, we're seeing like the sacroiliac joint. That's what is a thing we can look at, right? So the sacroiliac joint is well defined. You can see where we have the sacrum. You can see where we have the ala here of the ilium, right? And so you can actually even see the joint space itself. You can see some bowel gas. You can see everything. But when we look at the 64 by 64 matrix, you can't see that. Because whereas there may be hundreds of pixels in this tiny area that can define each individual shade of gray, over here there may be 10, 20 pixels, and all of these 100 pixels will now be averaged in A as 10 pixels. And so when you look at it, you can't define these areas because they're averaged together into larger blocks. When we look at this image on A back in the day when we were coming up with certain things in digital photography, even, an image like this would be called pixelated, right? You've heard that term, pixelated. It's not, the pixels aren't well defined. Well, that's what's happening is we have well-defined pixels because we have so many here. Over here, if we take the same image, there's not as many pixels, so it gets a little blurry, right? That's what we're seeing, the pixelation, okay? That's why when we have a larger matrix with smaller pixels, that equals lower pitch, all of that equates to better spatial resolution. When we look here, when we're looking at things here, we're looking at cassette sizes in a matrix. All right. And so with cassette sizes in matrix, what we're seeing is that some manufacturers create cassettes that have the same amount of pixels, even if we have a different size of detector, okay, or a size of receptor. And so what the case is making here is that when we have smaller cassette sizes, we have better pitch if we have the same amount of pixels in those detectors. And so what that means to us is we want to use smaller cassette sizes if we have the ability to. When we talk about contrast resolution is a different term. It's going to be the ability to detect visual differences. CR and DR themselves have superior contrast resolution, okay, due to the dynamic range, which is the number of shaded grays an imaging system can reproduce, okay? And so when we deal with contrast resolution, what we really are looking at is going to be bit depth, okay? Because that is linked with grayscale. The bit depth allows for us to see differences in shades of gray. So the way we can compute this is by this equation, 2n, where n equals the number of bits, okay? And so that n number can range anywhere from, a 1 to whatever number. Typically in a digital imaging system, uh, we see 8 to 32 bits, okay? No matter how many shades of gray are produced, the human eye can only distinguish between 30 of those shades. And so now when we see here, this is 1 bit, right? And so 2 to the power of 1 is 2. And so when you look at that, you're seeing the 2 shades here, okay? Now when you're seeing it, you're seeing black and white shades, okay? Here, 2 to the power of 4, right? 2 to the power of 4 is 2 times 2 times 2 times 2. And so we see 16. Now you can see the 16 different shades here. And then here's 8-bit, and we're able to see an image that we're used to. Okay. Modulation transfer function. It's the ability of digital systems to acquire and record information accurately. Now, smaller objects are harder to image than large objects. Okay. And so the reason, and remember, we go back to the pixel size being a limiting factor, is say this is a piece of information on a person's body that we want to record. And this is the actual pixel or detector element itself. When you look at this black dot here, we can only image the entire pixel, right? So that means that this black dot, the shade is going to average all of this whitened area as well. And so the only way we could record this piece of information is if the black dot was bigger than the pixel, right? Because then the entire pixel would be black. But as it's shown here, it's going to have to average this black dot with all these white areas. And so when it presents itself, it's going to show up as a shade of gray. We wouldn't even know that there's a black dot there. And so that's why smaller objects are harder to image, okay? No system, again, can image smaller than the pixel size or the detector element itself. The MTF of 0 means that we cannot record the information, and MTF of 1 means we record the information properly. And so when we talk about that, in general, the MTF of an image that we're taking will never be 100% accurate, okay? Because we are taking, say, a hand and trying to replicate it on a 2D surface. Our hand is 3-dimensional. And so it will lose information and value across getting transferred to our detector. And so a MTF will never be 1. But the closer an MTF is to 1 means we are able to accurately record the information that we provide our systems. With image signal, the way I talk about it, signal itself is the image portion that we are trying to establish, okay? Noise is that random information that contains no anatomical information. And so there's a term that comes out that's signal to noise ratio, and it's just how it sounds. The signal compared to the unwanted noise. And so when you think about it, we obviously want high signal to noise ratio. And so that's achieved by selecting appropriate technical factors. And so when we talk about signal to noise ratio, the technical factors that we establish, we have to understand that portion, right? That we want a high SNR. And so If our noise is high, that means we don't have the right technique. So that means we need an increase of technical factors to get a better high SNR. Contrast to noise ratio, CNR, it's the ability to produce a useful image to see the visibility of a structure versus the noise. And so in the same case, we want higher contrast than noise. Noise is something we want to avoid, right? Because this is what it looks like. That quantum model or quantum noise. The noise that we see is this grainy effect. You might hear people call that, or a salt and peppery effect, right? The term quantum noise is the one we use. And so whenever we have quantum noise, we need to increase our technical factors. Typically, we will see an increase of MAS for that, okay, to get a better image. As you can see in A, it had quantum noise. Image B doesn't, because we increased the MAS to allow for us to get a better image. When we talk about DQE, detective quantum efficiency, when we talk about DQE, this is basically a measurement of how our system can convert the X-ray that we give it to an image that we see. And so when we talk about it, amorphous selenium has the highest DQE. There's no light conversion step. And so the higher the DQE system that we have, the less dose we need to create an image. And so 100% efficiency is no loss of information and a DQE of 1. But just like with MTF, we can never have a efficiency of 100%. Okay? And so the higher our DQE is, the better it is. But we'll never reach 100% efficiency. When we talk about digital radiography, radiography in general has moved away from film to digital. There's two different types of digital radiography. Again, computed radiography and direct radiography. Computed radiography is like before, where we have to process an imaging plate. So we have a step that we have to do. It's more time consuming for CR. With DR, what we're seeing, an image is shown directly after capture. Okay, it can be further broken down into two types of systems: direct conversion, indirect conversion. With direct conversion, converting X-rays directly into charge; indirect, converting X-rays first to light, and then the light to the electrical charge. But in the DR systems, it's direct, meaning it'll go directly from capture to our monitors. Okay, in the CR step, we're going to have to process the plate, and then it gets run through a processor, and then it appears on the screen. So there's a difference between those two. When we talk about computed radiography, what we're seeing is there's a variety of different steps in the layers of what needs to be in a CR plate. But the main one is our phosphor layer. This is the active layer. This is the layer that stores our images. The latent image is stored in this area. This layer is made out of barium fluorohalide crystals. And so information can be stored in this layer for several hours, but slowly the image dissipates. So we need to process our plates when we are doing imaging. We shouldn't leave an image on a plate for so long. And there's a variety of basic steps in computed image formation, and we're going to go over them. And this should be, again, a rehash of material. The first is we expose our plate, and so the latent image is then stored on those barium fluorohalide crystals. We will need to then place the image we will see the imaging plate get exposed by an infrared laser light once it's inside the processor. Okay, it's going to be stimulated. That laser will relax all the electrons held within that phosphor layer. Once that happens, the electrons are relaxed, they emit a visible blue light. That light is picked up by what's called a photomultiplier tube, and that light is letting our latent image be visible. Okay. In this layer, there can be a step, there can be a lot of loss of information because the light is being released. Is our photomultiplier tube picking up the information? All right. So this is where some of information can be lost. And then in the erasure stage, what we are seeing is once the latent image has been read, we are seeing an intense white light, okay, being shown across. And so that intense white light will remove any residual photons and electrons, I should say, that will allow for us to see the image, okay? Now, with direct radiography differs from CR because it communicates directly with the workstation, meaning once you capture the image, it will go directly to a monitor. Okay, this produces images much quicker than CR systems. Direct conversion detectors use photoconductors that convert X-ray into electronic signal directly. Indirect conversion detectors use scintillators, which convert X-rays into light. There's an extra step with indirect conversion, so there's also loss of information that can occur in that step. Analog to digital converter converts our analog signal to a digital information. Okay, so that's what we see. So direct conversion detectors, those are those amorphous selenium and thin film transistor detectors. And again, if you remember with DQE, those have a lot of quantum efficiency, right? Remember, amorphous selenium has the highest DQE. Indirect conversion is with a scintillator and amorphous silicon and a scintillator and charge coupled device. So that's what we can see with those. Now with flat panel detectors, that's what we call these amorphous selenium detectors. These are sometimes referred as direct DR. It eliminates the need for a scintillator. The thin film transistor is what is used to read out our information. The TFT acquires electrical charge, the thin film transistor, as an array of or matrix of detector elements. So the detector elements are found on the detector, and that's what we're seeing. The detector element is the area of our detectors that can be used to capture our image. They can be small and pixel sized. The size itself cannot be changed. It's set by the manufacturer. What we know, though, is the smaller that detector element, the higher the spatial resolution. Another factor that contributes to spatial resolution is the fill factor of the detector element. And so the fill factor, this is what we're seeing here, of the detector element is seen. And so what we see is usually about 50 to 80% of a detector element will be sensitive to X-ray. The higher the fill factor, the higher the spatial resolution. And so why the fill factor is usually 50 to 80% is because it couldn't be 100%. There has to be some way we can transfer that information to our computers, right? So that's that thin film transistor. There's also a storage area in case we need to store some of that information here. And so there's always going to be some areas that won't be sensitive to X-ray. But the higher percentage of sensitivity to X-ray our detector element is, the better the resolution. How that presents itself is here. You can see here is a low fill factor. This is our sensitive to X-ray part. Notice how it's a little blurred. Here is a larger fill factor that's sensitive to X-ray. Notice how clear and sharp that area is, okay? With the charge coupled device, the CCD acts as a photodetector. It converts light into electrical charge. That's a cesium iodide or gadolinium oxysulfide-based scintillator. These are relatively inexpensive versus flat panel systems, okay? Their design itself makes it easier to repair. When we talk about CMOS systems are the newest type of system. They have a pixel or detector element amplifier, okay, that gets switched on and off by its circuitry within the pixel. So these systems are highly efficient and inexpensive. They take up less space than the CCDs. They use little to no power when not needed. However, they're more susceptible to noise, and the light sensitivity with these systems are lower than CCD systems. I used the textbook to get a little bit more information on the differences, so you can read these yourself. They basically state the differences between a CMOS and a CCD system because they are both indirect conversion processes. And the last thing that we have for the agenda is our digital detector care. All right. And so when we talk about digital detector care, it's important to understand that these are expensive pieces of equipment. Okay. Um, we need to take care of these pieces of equipment. Since they're electronic, fluid could leak and even damage the inner electronics of this cassette. And so some panels have weight restrictions of 500 pounds. And so we need to be mindful of this, and we need to protect our detectors because some areas they don't have 800,000 I shouldn't say 800,000 $80,000 laying around to replace a detector. Okay, and so we need to be mindful of that. All right, guys, other than that, that's the end of our lectures. A couple things. I see somebody that has or logged in with their phone. Please send me an email. I cannot grant you credit because your name doesn't appear. So please send me an email that you are you. So that way I can give you credit for attendance of this lecture. You don't have to write a lecture summary because you have been in attendance. So anybody here, you don't have to submit anything. You don't have to say I attended lecture. I'm about to grade those pieces now, okay? So you don't have to put anything in. Couple other things, stay on top of all your assignments so that we can see, that portion. I actually am going to go back to grade the quizzes because there is a portion that needs to be manually graded. So you're going to see those pretty shortly. I'll be grading those here. Other than that, guys, sorry for the past 2 weeks. It's been crazy in Houston with the hurricane and, recovering from that. There's been a lot going on in and around with my program. So we've had to, shift things around. But other than that, guys, take care. Anytime you guys need anything, you can always email me. I'm really quick to respond to emails. So send those emails to me if you have anything. But other than that, guys, take care. I'll see y'all next week. Bye.